Welcome back to the Quantum Space podcast, Innovating Trust. This is episode 7, and today we're exploring a theme that may well define the future of cybersecurity. Stranger physics, stronger security, how the weirdness of quantum mechanics is becoming cybersecurity's strongest defense. For decades, digital security has relied on mathematics. Encryption was strong because it was computationally hard to break. But with quantum computing fast approaching, those assumptions are starting to look fragile. Algorithms we've trusted for years could become vulnerable. Here's the remarkable twist. The very quantum mechanics that pose the threat also hold the solution. In our latest white paper, we unpack 7 principles of physics from the Copenhagen interpretation to no cloning, entanglement, Bell's theorem, uncertainty, decoherence, and quantum randomness. Each of these once mysterious ideas is now being engineered into real-world security systems that even a quantum computer can't crack. In this episode, we'll walk through how these principles work, what they mean for finance, government, healthcare, and critical infrastructure, and why the so-called weirdness of quantum physics has become our strongest shield for trust in the digital age. So let's do a deep dive into stranger physics, stronger security.
Imagine a world where your most sensitive data isn't just protected by complex algorithms, but by the very laws of physics themselves. Sounds like pure science fiction, right? Well, today, we're diving deep into a topic that's actively making that future a reality. Our mission on this deep dive is to explore how the incredible, often bizarre principles of quantum physics are becoming the new firewall for cybersecurity. The aha moment we promise you today is a clear understanding of how the truly weird aspects of quantum mechanics, the ones that even puzzled Einstein, are now being engineered into uncrackable, future-proof defenses for our digital world. We're going to give you a shortcut, basically, to understanding this paradigm shift from math-based to physics-based security. This deep dive is based on a compelling white paper titled Physics as the New Firewall, which lays out 7 key quantum principles. Okay, let's unpack this. The central theme here is that the very weirdness that once confounded physicists is now being harnessed to create tamper-proof defenses for the digital age.
We're talking about principles like the Copenhagen interpretation, the no cloning theorem, entanglement, Bell's inequalities, uncertainty, decoherence, and quantum randomness. Ready to jump into the quantum realm. First up is the Copenhagen principle. It's this kind of mind-bending idea that in the quantum world, simply observing something isn't passive. It fundamentally changes what you're looking at. So how on earth can something so abstract possibly serve as a security alarm for your data?
That's the million-dollar question, isn't it? It feels completely counterintuitive, but the magic lies in superposition. Imagine a quantum particle, like a photon, existing in multiple states simultaneously, say, polarized both horizontally and vertically at the same time.
Okay, so it's in both states at once.
Exactly, until you measure it. When you measure, you force it to choose just one definite state. That collapses the superposition.
And that collapse is key.
It is. Crucially, this measurement is irreversible. What's fascinating here is how this radical idea becomes a security mechanism. Unlike classical cryptography, which, relies on computational difficulty, quantum cryptography roots its security in the physical impossibility of silent eavesdropping.
Exactly. And the genius of quantum key distribution, or QKD, is how it leverages this observation as detection principle. Take the BB84 protocol, for instance. Can you walk us through the basics of how it works, and maybe just, the simple version?
Certainly. Picture Alice wanting to send a secret key to Bob. She encodes her bits by preparing photons with specific polarizations. For example, vertical for call a 0 and horizontal for a 1 in one set of bases, and then maybe diagonal for a 0 and anti-diagonal for a 1 in another.
Okay.
She sends these photons to Bob. Bob randomly chooses which bases to use for his measurements. He doesn't know which basis Alice used for each photon.
So he's guessing the settings.
Right. After Bob measures all the photons he receives, they get on a public channel, like a regular phone line, and compare only the bases they use.
Not the actual bit values, though.
Absolutely not, just the bases. If their bases match for a particular photon, they keep the resulting bit. If they don't match, they discard it.
Got it. So where does the security come in?
The critical insight here is Eve, the eavesdropper. If Eve tries to intercept those photons, she must measure them to learn anything. But her measurement, thanks to the Copenhagen principle, inevitably disturbs the quantum state.
because observing changes it.
Precisely. Alice and Bob will then detect these disturbances as errors when they compare a small, randomly chosen subset of their retained bits. So QKD doesn't prevent interception, but it guarantees you'll know if it happened. It makes silent key theft impossible. It secures the key exchange.
That's a huge shift from classical security. And we're not just talking theory here. This is being deployed. I mean, the DARPA quantum network was operational way back in 2004.
Early days, but significant.
And the SECOQC project in Vienna secured communications for banks and government agencies in 2008. More recently, China's MISSIS satellite, launched in 2017, showed us long-distance QKD across thousands of kilometers.
Yeah, the satellite work is really pushing the boundaries.
And commercial solutions are available now from companies like ID Quantique, Toshiba. Think about the impact for banking and finance, securing SWIFT messages.
Huge potential there.
For government and defense, protecting command and control systems. For healthcare and pharma, safeguarding patient data, intellectual property, even critical infrastructure like energy grids.
However, it's not without its challenges. Let's be clear on that.
Right, the practical side.
Implementing QKD often requires dedicated optical fiber or satellite links. That isn't cheap, and it limits scalability for now. Fiber-based systems are currently limited by photon loss over distance maybe a few hundred kilometers. Satellites help extend that, but add complexity.
And getting it to work with existing networks.
Exactly. Integrating these new quantum layers with existing classical networks requires careful, sophisticated engineering. It's not plug and play yet.
Okay, so we've seen how observation itself becomes an active guardian. Now, let's turn to something maybe even more profound. What if copying itself was physically impossible? This brings us to the no cloning guarantee. In our digital world, copying is effortless files, keys, databases. You just hit trill plus C.
Right. It's trivial.
But the quantum world has this fundamental, almost magical barrier against it.
It's truly mind-bending. The no-cloning theorem states that an arbitrary, unknown quantum state cannot be perfectly duplicated.
Cannot be perfectly duplicated.
Correct. It's like trying to photocopy a unique thought. Any attempt to replicate it inherently changes or destroys the original state. And this isn't just a tech limitation, it's a fundamental law baked into the linear nature of quantum mechanics. So this raises an important question. Why is this such a game changer for cybersecurity?
Well, it's incredibly significant, right? Because it means quantum keys cannot be silently harvested for future cracking. In classical crypto, an attacker can just copy encrypted data, store it, and wait. Wait for a powerful enough computer, maybe a quantum computer, to break it later. The store now, decrypt later attack.
A major looming threat.
But with quantum communications, an attacker cannot copy the quantum states carrying the keys. Any attempt either destroys the state or alters it detectably. The key takeaway here is that security is based on this physical impossibility, not just on computational limits that might, eventually be broken.
Precisely. In those QKD protocols we talked about, like BB84, if Eve tries to copy photons, she has to measure them first. That act of measurement collapses their delicate quantum state. The copies she creates and forwards are then just her best guess, based on her measurement. And this process inevitably introduces detectable errors into the key that Alice and Bob will spot when they compare notes.
So the no-cloning theorem really underpins that whole detection guarantee.
It's the bedrock, yes.
From a business perspective, this translates into powerful strategic assurances. It offers real future-proofing against quantum attacks. No more store now, decrypt later worries for data protected this way.
That's a huge selling point.
Organizations gain unwavering confidence in their secure communications, knowing interception is inherently visible. It creates a competitive differentiation offering clients physics-backed confidentiality.
Absolutely crucial for high-stakes areas. Financial transactions, diplomatic channels, critical national infrastructure.
And we see this in action with pilot projects like the EU's EuroQCI and China's MISSIS satellite. They rely on this fundamental guarantee.
Of course, the practical limitations we mentioned still apply. Photon loss, distance issues with fiber, the cost and expertise needed for integration. It's getting better, but still hurdles to overcome.
Okay, now for something really wild. Entangled security. We're talking about harnessing what Einstein famously dismissed as spooky action at distance. It sounds like a paradox, a deep mystery, but somehow it's become a cornerstone for digital trust. How did something so, spooky become a tool for building trust?
It is spooky. Entanglement happens when two quantum particles, like photons, are created together in such a way that their properties remain linked or correlated no matter how far apart they fly.
Linked instantly.
Instantly. Measure one, and you instantaneously know the state of the other, even if it's light years away. And the correlation is stronger than anything possible classically. There's no hidden information, no secret copy telling them what to do. They genuinely share a single unified quantum state. If we connect this to the bigger picture, entanglement is like a trust mechanism built right into the fabric of nature. It creates a connection that cannot be faked classically.
So how do we actually use this for security? There's a specific protocol, right? Eckert 91?
Yes, the Eckert 91 protocol puts entanglement front and center.
How does that work for Alice and Bob? How do they use entanglement for a key?
In Eckert 91, instead of Alice sending photons to Bob, there's a central source that generates pairs of entangled photons. It sends one photon from each pair to Alice and the other to Bob.
Okay, so they each get half of a linked pair.
Exactly. Then, like in BB84, they each measure their photon using randomly chosen measurement bases. Because the photons are entangled, their measurement outcomes will be strongly correlated.
More correlated than classical physics allows.
Much more. They then publicly compare a small subset of their results. But here's the twist. They're not just looking for errors caused by an eavesdropper. They're testing if the correlations themselves violate what are called Bell's inequalities.
Bell's inequalities.
Ooh.
We'll get to those next, I think.
We will. But the point here is, if they see correlations strong enough to violate Bell's inequality, they know they're dealing with genuine quantum entanglement, and Eve can't be spoofing it classically. If that checks out and errors are low, they can extract a secure key.
So the security is rooted in verifying these non-classical correlations. It's not just about detecting disturbance.
Precisely. It adds this powerful layer of authentication. You're confirming the quantum nature of the resource itself.
That sounds incredibly powerful. What are the advantages?
Well, authentication of quantum resources, as we said, confirming genuine entanglement. It also opens the door to something called device independence in more advanced schemes.
Device independence, meaning you don't have to trust the boxes.
Essentially, yes. Security doesn't rely entirely on trusting the internal workings of Alice's and Bob's hardware. And for reach, satellites can distribute entangled photons over vast distances, thousands of kilometers, enabling truly global quantum secure networks.
We saw that with Meshius, right? Distributing entangled photons over 1,200 kilometers.
Exactly. And researchers are developing quantum repeaters that use entanglement swapping, not copying, to extend network reach even further. Device-independent QKD is another major research direction using entanglement.
Still facing challenges, though, I assume.
Oh, yes. Photon loss is still an issue. Entanglement is very fragile. It suffers from decoherence over long distances. The infrastructure is complex and expensive, and scaling these networks remains a significant hurdle.
Okay, this brings us perfectly to Bell's proof, verifying quantum security using physics itself. You mentioned Bell's inequalities. Back in 1964, John Bell asked this profound question. Were these weird quantum correlations really quantum, or could they be explained by some deeper hidden classical rules, hidden variables?
Right. It was a fundamental debate about the nature of reality. What's truly remarkable here is how Bell didn't just ask the question. He figured out a way to test it. He developed a mathematical test, Bell's inequality, that sets a limit on how strong correlations could be if they were based on underlying classical physics or hidden variables.
The limit for the classical world.
Exactly. And experiments have shown, definitively, especially with the loophole-free tests around 2015, that quantum entanglement violates this inequality. The correlations are stronger than any classical explanation allows.
So it proves entanglement is genuinely quantum, not some hidden classical trick.
Correct. It's like a mathematical lie detector for quantum states. If entangled particles violate Bell's inequality, you know they're the real quantum deal.
And how does this abstract physics become a security audit tool?
In entanglement-based QKD, like Eckert 91, Alice and Bob don't just use entanglement, they run this Bell test on their results. By checking if their measurements violate Bell's inequality, they achieve several things. They confirm they have a genuine quantum source, they prove no classical adversary could be spoofing the correlations, and critically, they verify that their secret key generation process is secure.
So it's verification baked right into the physics.
Precisely. And one of the most powerful applications of this is device-independent QKD, or DIQKD.
You mentioned the idea of not having to trust the hardware.
Yes. The problem with standard QKD is it assumes Alice's and Bob's devices work exactly as specified. But what if the hardware is compromised? A supply chain attack, for example.
A huge concern in security.
Absolutely. DIQKD aims to remove this need for trust. Alice and Bob just need to perform measurements and run the Bell test on their outcomes. If the results violate Bell's inequality, they know they're generating a secure key based on genuine quantum entanglement, regardless of what's happening inside the potentially untrusted devices. Security depends purely on the observed statistics violating a law of physics, not on trusting vendors.
Wow. The implications are profound. Security is tested, not assumed. Resistance to supply chain attacks. Unprecedented transparency.
Yeah, major leap.
So what does this all mean? It feels like a fundamental shift. We're moving from trusting systems and vendors to trusting the laws of physics itself.
That's the core idea. It's revolutionary for telecoms, government, defense, international finance, anywhere that needs verifiable, tamper-proof security.
Still challenging to implement, though.
Definitely. Current DIQKD implementations are often less efficient, have shorter ranges, and are more complex than standard QKD, but the security promise is enormous.
Okay, let's switch gears slightly to uncertainty as security. We all know Heisenberg's uncertainty principle from popular culture, usually meaning things are fuzzy or unknown. But in quantum crypto, it's apparently an absolute guarantee of security. How does unpredictability become a shield?
Yeah, the pop culture version is a bit misleading. The physics of uncertainty isn't about fuzziness or faulty instruments. It's a fundamental limit imposed by nature. For certain pairs of properties, physicists call them conjugate variables, like position and momentum, or a photon's polarization measured in two different incompatible bases. You literally cannot know both precisely at the same time.
I can't know both. Why not?
Because the very act of measuring one property with high precision inevitably disturbs the other property, making it less certain. Perfect simultaneous knowledge of both is fundamentally forbidden by quantum mechanics.
Okay, so how does that translate to crypto, like the BB84 QKD protocol we discussed earlier?
It's crucial there. Remember, Alice sends photons polarized in different bases, and Bob randomly chooses bases to measure them.
Right.
If an eavesdropper, Eve, intercepts a photon and tries to measure it, she also has to guess the basis. If she guesses the wrong basis, the uncertainty principle guarantees her measurement will disturb the photon's state in the other basis.
Measuring in one basis scrambles the information in the other?
Exactly. So when Bob later measures that photon, even if he uses the correct basis Alice intended, there's a chance he'll get an error introduced by Eve's incorrect measurement.
So Eve's snooping leaves a fingerprint.
A statistical fingerprint that simply cannot be hidden. Interception inherently leaves an unavoidable trace because of this fundamental uncertainty.
Why is this principle so vital for security, then?
Well, it offers guaranteed detection. The security rests on a natural law that nobody, no matter how clever or powerful, can bypass. It also directly prevents those store now, decrypt later attacks. Since Eve can't measure the quantum state perfectly without disturbing it, she can't make a perfect copy or record of the quantum key for future cracking.
So it provides built-in resilience.
Absolutely. Uncertainty, surprisingly, becomes a strategic asset in cybersecurity. It protects sensitive communications like diplomatic messages or patient records from being compromised years down the line by future decryption capabilities.
Makes sense. So applications are, again, in finance, national security, healthcare, protecting data where long-term confidentiality is paramount.
Correct. The main challenges are similar. Distinguishing the errors caused by Eve from natural noise in the channel, the infrastructure needs, and integrating these systems smoothly.
And future directions here.
Things like measurement device independent QKD also leverage uncertainty principles to remove trust assumptions about the measurement devices themselves, offering yet another layer of physics-based security. Also, new quantum secure authentication methods are being built on this.
Right. Let's move to decoherence. This often sounds like the enemy of quantum tech, right? It's the process that makes quantum states fragile, the loss of quantumness.
Yeah.
But paradoxically, the white paper says it's also a security feature. How can a limitation possibly be a strength?
It's definitely a double-edged sword. Decoherence is the process where a delicate quantum state like a superposition or entanglement loses its unique quantum properties, its coherence, due to interactions with its surrounding environment.
Like noise messing things up.
Exactly. Think of it like vibrations disturbing a perfectly still pond, ruining the clear reflection. The quantum system starts to leak information to the environment, loses its superposition, and behaves more like a classical object. It's why building quantum computers is so hard. You have to isolate them perfectly.
Okay, so how does this matter for security? First, the downside.
The downside is clear. Decoherence limits the distance quantum information can travel, especially in optical fibers. It causes photons to get lost or have their states scrambled. This restricts fiber-based QKD to typically a few hundred kilometers. It also introduces errors into the quantum channel that can look very similar to the errors caused by an eavesdropper.
So it makes it harder to tell if it's just noise or if someone's listening in.
It can, yes. But here's the paradoxical advantage. The reason quantum states are so sensitive to environmental interaction, decoherence, is the same reason they are sensitive to an eavesdropper's interaction.
Okay. So the fragility cuts both ways.
Precisely. Any attempt by Eve to intercept and measure the quantum state is an interaction with the environment from the photon's perspective. It will inevitably cause decoherence or disturbances, just like natural noise does. So, while decoherence is a nuisance that limits distance and adds noise, that very sensitivity is what ensures eavesdropping cannot be perfectly hidden. It guarantees that interaction leaves a trace.
The key takeaway then is decoherence is the price you pay for quantum sensitivity. But that sensitivity is also what makes QKD inherently secure against undetected attacks.
You've got it. Protocols are designed to handle this. They establish a baseline error rate expected from natural decoherence and channel noise. Then they use techniques like error correction and privacy amplification.
Privacy amplification.
It's a mathematical process Alice and Bob use after their initial key exchange. They essentially distill a shorter but perfectly secret key from the longer, slightly noisy key they first generated. Sacrificing some length to eliminate any potential information Eve might have gained, they can overcome expected noise levels.
So managing decoherence is about balancing that sensitivity with resilience.
Exactly, finding that sweet spot.
And are there ways to fight decoherence to extend the range?
Yes, absolutely. This is a huge area of research. One key technology is quantum repeaters.
Not like classical repeaters that just amplify a signal, right?
Right. No, because you can't copy a quantum state. Quantum repeaters work differently. They typically use concepts like entanglement swapping and quantum memory. Imagine breaking the long distance into shorter segments. The repeaters create entanglement between adjacent segments and then perform a special measurement to swap the entanglement across the gap, effectively extending the entanglement over the full distance without ever measuring the qubit carrying the secret key directly.
Pretty complex stuff.
Very. And quantum error correction codes are also being developed. These encode the information of one logical quantum bit across many physical quantum bits. So if one or a few physical bits decohere, the overall logical information is still protected.
Where are we seeing applications dealing with decoherence now?
Well, satellite QKD is one approach, as decoherence is much less of an issue in the vacuum of space compared to optical fiber. MISHI's demonstrated this. Metropolitan quantum networks operating over city scales can manage decoherence effectively within current fiber limits. And future networks will likely be hybrid, using satellites for the long-haul links and fiber for the final connection to users.
What's the business impact here, thinking about these trade-offs?
It involves careful cost versus security calculations. Do you deploy QKD now over shorter distances or wait for repeater technology to mature for longer links? It requires sophisticated risk management to accurately distinguish those inevitable background error rates from actual security breaches.
And standardization is probably key, too.
Crucial. Standardizing error thresholds, repeater protocols, integrating all of this with classical post-quantum cryptography. Lots of work still ongoing.
Okay, last principle. Perfect randomness. This feels fundamental. All strong cryptography relies on good randomness, right? But the problem with classical pseudo-random number generators, PRNGs, is that they're based on algorithms. They seem random, but they're ultimately deterministic. Predictable if you know the starting point or the algorithm.
Absolutely. That predictability is a potential Achilles heel for classical security. If an attacker can figure out the random numbers used to generate keys or nonces, the whole system can collapse.
So how is quantum randomness different?
What's fascinating here is that quantum randomness is fundamentally different. It offers intrinsic, irreducible unpredictability. It's not pseudo-random, it's genuinely random, dictated by the probabilistic nature of quantum mechanics itself.
How does that work?
Think about a simple quantum measurement, like sending a single photon towards a beam splitter, a half-silvered mirror. Quantum mechanics says there's a 50-50 probability it will be reflected and a 50-50 probability it will be transmitted. Before the measurement, it's impossible to know which path it will take, not just practically, but in principle. Even with complete knowledge of the system, the outcome is inherently probabilistic. It's like nature rolling a perfect, unbiased die for every photon.
So it's not just hard to predict, it's impossible to predict.
That's the core idea. This ensures that the randomness feeding into cryptographic processes is truly unassailable, even against future quantum computers or attackers with unlimited computational power.
And we have devices that do this now. Quantum random number generators, QRNGs.
Yes, QRNGs are a maturing technology. There are various types. Some are photon-based, using beam splitters, like the example I gave. Others use phase noise, exploiting tiny random fluctuations in the light from a laser to generate randomness at very high speeds. And importantly, we're seeing integrated chip-based QRNGs being developed, small enough to potentially fit into smartphones or IoT devices.
Why is this true randomness so crucial for security?
It provides fundamentally stronger encryption keys that cannot be guessed, predicted, or reverse engineered by analyzing the generator. It enables more secure authentication methods using truly unpredictable tokens or challenges. It also offers protection against hitting back doors in random number generation because the quantum process itself is, in principle, verifiable based on physics, unlike complex algorithms. And ultimately, it delivers future-proof resilience. The randomness is secure against any adversary, present or future.
Where are these QRNGs being used?
They're finding applications across many sectors. Financial services use them for generating high-quality encryption keys for secure transactions. The telecom industry is integrating QRNG chips into secure hardware modules. Healthcare and pharma can use them to protect sensitive patient records and intellectual property from those store now, decrypt later attacks by ensuring keys are truly random. National security agencies rely on them for the highest levels of secure communication. And as I mentioned, the potential for consumer devices is huge.
What are the hurdles for QRNGs?
Well, you need specialized hardware, obviously. Verification is also important, ensuring the output is genuinely dominated by quantum randomness and not just classical noise in the system. This leads to research in device-independent QRNGs, similar to DIQKD. Integration into existing systems needs careful handling, and cost is still a factor, although it's coming down, especially with chip-scale devices. But the outlook is incredibly promising. We're seeing standardization efforts from bodies like ETSI and ISO. Miniaturization is advancing rapidly. We can expect QRNGs to become increasingly common, perhaps even ubiquitous, as part of the infrastructure for the future quantum internet.
Wow, what an incredible journey we've taken today. It's really something. We've gone from these concepts that sound like pure theory, superposition, entanglement, uncertainty.
Things that baffled the pioneers of physics.
Exactly. And seeing how they're transitioning from labs into becoming the frontline tools of cybersecurity. The core message here feels undeniably clear. This isn't just tweaking algorithms. It's a fundamental transformative shift. Moving from security based on math problems we hope are hard to security enforced by the actual laws of physics.
Laws we believe are immutable.
Right. This weirdness of quantum mechanics is genuinely being engineered into a new kind of firewall, an immutable one perhaps for our digital lives. So for you listening, you hopefully now have a much deeper grasp at why these quantum concepts aren't just scientific curiosities. They matter profoundly for protecting data against today's threats, and crucially, against the threats of tomorrow, offering resilience that math alone might not guarantee.
And it's worth stressing again, this isn't just an incremental improvement like a faster chip or a slightly better algorithm. It represents a fundamental change in how we establish trust and ensure security in a digital world that's facing the unprecedented challenge of quantum computing.
Security enforced, quite literally, by the fabric of the universe itself.
Couldn't have said it better.
So here's a final thought to leave you with. As our digital lives become more and more intertwined with these fundamental quantum principles, how might our very perception of what trust and security even mean actually change? What does it truly mean for the future of information when the most abstract, counterintuitive laws of the universe become our most tangible, potentially unbreakable guardians? Something to think about regarding your own data, the services you use, the future of technology. It's a profound shift, and it's happening right now. Thanks for joining us for this deep dive.
You've been listening to the Quantum Space Podcast, Innovating Trust, Episode 7, Stranger Physics, Stronger Security. If you'd like to explore these ideas in more depth, the full white paper titled Physics as the New Firewall is available now at thequantumspace.org. There you'll find all 7 principles of quantum physics explained and connected to real-world applications in finance, government, healthcare, and critical infrastructure. Thanks for joining us on this journey where physics and cybersecurity meet. Until next time, This has been the Quantum Space Podcast, Innovating Trust. This was Innovating Trust, a Quantum Space podcast edited and produced by Crown Communications.